Hey everybody, this is Mr. Beckstrom, and today we're going to take a look at section 3.2. This is on the derivative as a function. So in section 3.1, we really built up this idea of using limit to find the slope of the tangent line at some point on a curve. And really, we're just kind of transitioning into the idea that that's actually the same as the derivative at that point. So the derivative of f is the function. F prime of x, that means the derivative with respect to x, is equal to the limit as h approaches 0. Remember, that's the distance between your two x values. Of f of x plus h minus f of x, that's the difference of your two y values, all over h. And we showed last time how we really had like a plus h minus a, and the a's would cancel out there, just leaving us the h on the bottom here. And this says, provided the limit exists and x is in the domain of f, if f prime of f, the derivative, exists, we say f is differentiable at x. If f is differentiable at every point of an open interval I, we say that f is differentiable on I. So we can also find out if f is differentiable on some interval. Now, what does it really mean? Well, visually, let me give you an example here. So visually, if we have some kind of curve from point A to point B, differentiable means not only is this continuous from A to B, which means that we can take our pencil, start at whatever the A is, and get all the way to the B without lifting our pencil. That's the continuous. Differentiable is a stricter requirement. It means not only is it continuous, but it's also smooth. There's no sharp edges like this. There's no kind of weird dips like this. Basically, at every point on the interval from A to B, there's going to be a unique tangent line, right? If we had a jag like this right here, we could make an infinite number of tangent lines that just go through that one point. But if it's differentiable, that means that it's going to be smooth. At any point on that curve, you're only going to have one possible tangent line that goes through just that point. There's no other way to make that tangent, or there's no other slope of that tangent line, because it would then go through more than one point there. All right, so let's take a look at some examples here. All right, so for this first one here, I want to find the derivative of f with respect to x, so using this formula up here. And then after I find that derivative function, I want to evaluate it at both 2 and 4. So go ahead, see what you can do, and then we'll pause the video, and then we'll go through the solution. All right, so just up here a little bit, and so we're going to start just using this definition here. So the derivative with respect to x is equal to the limit as h approaches 0 of f of x plus h. That means we're just going to replace this function with x plus h. So that's going to be 4x plus h squared plus 1, and then minus f of x, so that's just the function there, minus 4x squared plus 1, all over h. And with all of these, we're going to soon realize that the first step is always to plug the 0 in there, but in this case, just about every case, we're going to get a 0 on top and a 0 on the bottom. So let's see what happens. If I put a 0 in here, notice that that becomes a 0. So this is really just 4x squared plus 1 minus 4x squared plus 1, which is 0 on top. And then you put in a 0 for the h, and that's 0. So that's the indeterminate form. So for all of these, we're going to have to keep going. And really, our main strategy is going to be somehow canceling out this h from the bottom. So let's go ahead and keep going. So if I'm going to kind of multiply this top out here together, this is going to be x squared plus 2xh plus h squared, and then everything is going to be multiplied by 4. So this is going to be 4x squared, and then we had the 2xh, so that would be plus 8xh, and then plus, that's the h squared, so that's going to be 4h squared, and then we have the plus 1, and then we have the minus 4x squared plus 1 all over h. And really, I'm going to go ahead and take these out and distribute that negative sign there, so that will end up being a minus 1 there. Alright, so now I have a positive 4x squared and a negative 4x squared. I have a plus 1 and I have a minus 1. And therefore, here I am left with just 8xh and a 4h squared. Notice that both of those terms have an h in them. So on my next one, and remember this limit stays the same, so we still have the limit as h approaches 0. I'm going to have the limit again as h approaches 0, and on the top I'm going to factor out an h, so that leaves me 8x plus 4h, and then on the bottom I have an h, and looky my h's cancel out. Now I can stick that 0 in there for h, and my derivative is just going to be 8x. So once I apply the 0, I do not write the limit anymore, so this is just going to be equal to 8x. So the derivative of 4x squared plus 1 using the limit definition is just 8x. Now I'm going to apply both 2 and 4. So a little bit up here. So f prime of 2 is just equal to 8 times 2, which is 16. And f prime of 4 is just equal to 8 times 4, which is 32. So the slope of the tangent line when x is equal to 2 is 16, and when x is equal to 4 is 32. All right, let's go ahead and move on to the next part of this here, and this is theorem 3.1. All right, theorem 3.1 says if f is differentiable at a, then it is continuous at a. And we can also take the contrapositive. Those of you who may have taken some kind of discrete math or other math class may have heard of the contrapositive. That's when we change the order. So this is if a, then b. The contrapositive would be if not b, then not a. So take the negation of the second part, put it first, and then take the negation of the first part. So if f is not continuous at a, then f is not differentiable at a. So we can also say that. And we really talked about that in the last example and showed that that differentiability is just a stricter requirement than continuity. So so something can be continuous without being differentiable. Let's take a look at that again. So if I were to ask you something like, show me a, we'll go from a to b, some function in the interval a to b that is continuous but not differentiable. You could do something like this, right? Because we still took our pencil without lifting it and went from A to B. However, at this point, we'll call that C, right? We are definitely not differentiable there because we can have an infinite number of tangent lines at that point. And in order for it to be differentiable, it has to be smooth, and we can only have one unique tangent line at that point. That's that. And then when is a function not differentiable at a point? So a function is not differentiable at a point if at least one of the following condition holds. It's not continuous, which we just kind of showed. It has a corner like this, right? Or it has a vertical tangent at that point. So if it has a vertical tangent line, if we remember about tangent lines, we know that the function never actually touches a vertical tangent line. So it can't be continuous or differentiable at that point. All right. Let's go ahead and take a look at another example here. Okay, here we see an example. It says, where is the function continuous? Where is it differentiable? It says use the graph of f, so this graph right here in the figure to do the following. Find the values of x in 0, 3, and which f is not continuous. Find the values of x in the intervals 0 to 3, at which f is not differentiable, and then they want us to sketch a graph of f. So go ahead and take a look at this, see what you can do, or excuse me, sketch a graph of the derivative f prime. So try it out, pause the video, see how you can do it, and then we'll take a look at it. All right, so for A, it says find the values of x in that interval 0 to 3 in which f is not continuous. So if I take my pencil and I start here at 0 and I go up, notice I have to raise my pencil and drop it here. So at 1, so for A, we can say x equals 1 is not continuous, but I can get all the way until the x value of 3 without lifting my pencil again. So it's going to be continuous every other place other than at 1. Now it says find the values of x in 0, 3 at which are not differentiable. So for B, we already know if it's not continuous, it's not differentiable, so not differentiable here. And we also have a corner there at x equals 2. So at a corner, remember, we can have an infinite number of tangent lines with different slopes. So it is not differentiable there, so also at 2, it is not differentiable. Now it says sketch the graph of f prime and try to graph the derivative of this function here. So I'm going to go along the same scale here. So we're going to go 1, 2, and 3. And we're going to see what's happening really with the slope of the tangent line at all of the points here. And it's going to be a little bit hard to see, but let's see what we can do. So starting off at x, sorry there. All right. Back there. Okay, starting off at x equals 0. Try this again. We notice that the slope of the tangent line is right there along it. So that's going to be a slope of 0. So on our thing here, we're going to go ahead and start at 0. Now as we move from 0 to 1, notice that, let me make that a little thinner here, notice that this tangent line as we move along goes from quite gradual. So as we go up a little bit, that's the slope right there. And then as we get closer to 1, we have a pretty steep slope. Maybe that slope is around 2. right? So we're going from gradual, that's a slope of 0, to around a slope of 2. So this first thing is just going to go straight from 0, 0 all the way up to 2 and stop somewhere around there. Now let's take a look at this next section here. Remember, we're just trying to kind of estimate the slopes of the tangent lines at all of these points here. So here, again, we're starting off maybe around a slope of 0 at x equals 1, and then we're going down this time. So we're kind of gradually going down, and then maybe we get a slope of around -1 or so when we get to x equals 2 there. You kind of see that going down. So this is going to start at 0, and it's going to like go down to like 2 there. And then the last one here, this is a pretty, oh gosh, I hate this tool here. It messes me up every time. All right. And just take a look at this last line here. Notice this goes straight up, pretty steep to the right. Maybe that's a slope of, you go up 2 over 1, up 2 over 1, because we start at 1 and we end at 3. So if that's a slope of 2 and it stays the same, that means we're going to go up to 2 here. We're going to go up to 2. And just stay at 2 until you get to 3 there. All right, so the graph of the derivative is just looking at what the values of the slopes are at every point. And remember, this is just an estimation, so you could do it a little bit differently and still be right there. All right. Well, that's all I have for this section. I have lots of examples too under resources. But if you have any questions, please let me know, and I hope you have a great weekend.